The aim of this lecture is to describe the smart agriculture, to give its definition, to name the enabling technologies and the factor affecting the farm technology adoption rate. After this lecture, you will be able to identify the major enabling technologies and the different factors affecting the decision of adopting those technologies. Precision agriculture, smart agriculture, or precision farming is an integrated farm management framework that constitutes a holistic management approach aiming to optimize the yield per unit of farming land, increasing the quality and quantity of agricultural output while using less inputs, water, energy, fertilizers, pesticides, etc., results in a cost reduction with positive environmental impact. So rather than applying the same amount of fertilizers over an entire agricultural field or feeding a large animal population with equal amounts of feed, the smart agriculture solution will measure the variation in the field conditions and adapt the fertilization or feed strategy accordingly. Farmers, as the principal stakeholders, usually make complex decisions without proper information and execute demanding field operations. Thus, smart agriculture solutions are best designed with the farmer at the center of the process, complementing and transforming the skills and experiences he gained naturally through the generations. The solution can complement and augment the farmer capabilities in three main sub-processes: data collection, where remote sensing and sensor networks are used; decision-making, where expert systems and machine learning can be exploited; and intervention, where intelligent machinery and robotic agents can be deployed for field operations. A typical complete process cycle would include data collection measuring, for example, moisture, pH, or multispectral images, followed by data analysis that produce description maps for pesticides, irrigation, fertilizers, or harvest, and finally, automated intervention executing the description maps on the field using variable rate technology machinery. This cycle can have variants addressing a single area of concern, such as the soil, the vegetation, or the environment. In addition to these farm-related sub-processes, smart agriculture can be designed to provide extra benefits for external functions, such as food traceability, soil and environmental monitoring, and specific bookkeeping facilitating national planning. These technologies are in different level of maturity and adoption worldwide. Hence, more than often, technology introduction to local communities needs to be planned and driven by the relevant authorities. Authorities working on analyzing and intervening in the markets must deal with consumers and overall social demands, ensuring proper performance and homogeneity of plans and positive aggregate indicators, such as inclusive growth, productivity improvement, environmental concern, in addition to food safety and security. However, deploying technologies or solutions should account for the wide diversity of agriculture through the African Union and its unique characteristics, particularly regarding farm size, types of farming, farming practices, yields level, and employment. This is the major innovation challenge. Technologies and solutions should be customized and adapted to the local context, considering that opportunities and concern can vary greatly. But what are the factors affecting technology adoption in agriculture? In general, smart agriculture solution adoption rate depends on: firstly, yield gap. Higher yield gain expected from the solution mean the yield profits might well pay off for the possible overhead costs. Secondly, the farm size, depending on the crop type and the technology involved in the proposed solution, large farms can have higher labor costs relative to small farms due to the need for information management specialists. And finally, the learning required to integrate the new technologies with existing practices. On the other hand, smart agriculture solutions affect the farm economics through multiple channels. Hence, solution design should evaluate the farm economics in different levels of analysis. For example, net returns and operational profits. The smart agriculture solution can reduce operating costs through optimizing the use of inputs. Even if input use and operating costs increase under precision agriculture, yields can grow enough to increase operating profits. Both effects should be reflected in operating costs and profits. The capital expenditures needed to implement precision agriculture technologies could raise the overhead costs, but at the same time enables farmers to substitute capital and labor for operating inputs, which can have spillovers and direct social impacts within the economy of production, reducing the profit leaks to imports of fertilizers. Capital to labor ratio should also be analyzed for the specific solution, since technology adoption might dictate a new skill set requirement for the workers, generate demand for new workers, or displace some of the old working force. Smart agriculture solutions are built on the several enabling technologies, including sensor technologies, global navigation satellite system GNSS, used for positioning, remote sensing, data storage and analysis, soil type, nutrient levels, variable rate technology, advisory systems and integrated communications, intelligent machinery, robotics, and autonomous navigation. Some of these technologies have recently seen relatively high investments and adoption rates in several agricultural applications and expected to lead the market in smart agriculture solutions.